Hi, what I want to talk about today was double replacement reactions. There's multiple steps that need to be done when we're doing fully all that we need to do with these. What I wanted to focus on at this point was how do you determine what products form, all right? So as we were classifying reactions in class, we know double replacements are two compounds reacting together, like these are, and then we need to be able to use our solubility rules to make sure that one of our products is a solid. If it doesn't make a solid, then it's not a double replacement reaction. So what we're going to focus on in this example is just how to predict the products. And then in the next video, we're going to look at how to write complete ionic and net ionic equations. All right, so when we take a look at our compounds, we have a cation and we have an anion part to this compound. The cations are going to switch places and have a new partner when they make their product. It doesn't matter which compound I write first, as long as I write the cation first, followed by the anion. And the clue to this is to bring one of each over. So it doesn't matter how many I have on the reactant side, just bring one of each over. I'm going to now switch the sodium over to a new anion, and he's going to hook up with the nitrate ion. Remember, 1 to 1. And I always say it's 1 to 1, check the charges. 1 to 1, check the charges. Because all I've done is bring them over, switch the partners, but I have not written a balanced compound yet. So I know that phosphate is a -3 because I have all those polyatomics memorized. I know the charge in silver is derived from the silver nitrate compound. Remember when we were naming them, we took a look at what the charge of the anion was, and the cation had to be that opposite charge to balance it off. So always go back to that compound to figure out what the charge is of transition metals. Once I do that, you know them to crisscross down to form a balanced compound. This over here with the sodium and the nitrate, we know sodium's a +1 because we can look at our periodic table. I have the polyatomics memorized that nitrate's a -1. It just so happened that it was written as a balanced compound to begin with. All right, let's go to problem number 2. I said we're going to switch cations here, hook them up to their new anion. So Fe is going to hook up to CO3. And I'm only going to bring one over, right? Even though I have 2 potassiums here, I bring just one over, and I hook it up with 1 chlorine. That's the key to it. 1 to 1, check the charges. All right, iron is a +2 because over here, with the total negative charge of chlorine, that's a -2. So iron has to be a +2. Carbonate is a -2. Just so happens that they balance each other charges out. Over here, potassium is a +1, chloride is a -1. Hey, it's my lucky day. I don't have to crisscross anything. They just so happen to be written as a balanced compound. Okay? Let's try this last one. Let's switch places between iron and sodium. Now, as you're looking at this video, why don't you stop and see if you can write the balanced compounds. All right, so I'm going to take iron, put it with its new partner, phosphate. I bring 1 sodium over. It doesn't matter that there's 3 on the other side. And I hook it up with the sulfate ion. Go back in and check those charges. I know phosphate's a -3. From this compound, I know sulfate's a -2, so iron had to be a +2. I'm going to crisscross those charges. So it's Fe3PO4 2 plus sodium's a +1, sulfate's a -2. Crisscross those to get to Na2SO4. Again, this is just an example of how to predict products. The next one's going to cover how to use solubility rules and how to be able to write complete and net ionic equations.